forces will be used in order to calculate reaction path profiles, so the Navier elastic band method to calculate rates in activated processes. Okay, so I'll talk about stress. Stress is useful. I mean, we are using when we deal with a solid. In principle, a solid is just a very big molecule, so there shouldn't be anything special in it. The equilibrium configuration is found when you put the system, let the force drive the system to the position of vanishing forces. That's okay. The problem is that if you think of a solid as a very big molecule, then basically every atom is different. You should use a very, very big unit cell. We lose periodicity because you have surface, and then you have to include also, I mean, you have your calculation of the process. So a useful idealization of a solid is the infinite and periodic crystal, which is what we all use, especially when you are using plane waves, because plane waves are actually very good in describing infinite system, and say you are making some approximation when you want to use a plane wave code to study a finite system. The advantage of plane waves, we have already said, is the periodicity. Then your crystal is periodic. You can use small unit cell, and the periodicity, the lattice periodicity allows you to use Bloch theorem. And in addition to the translational periodicity, then you have point group symmetry that allows you to reduce further the number of points. So this is one of the reason why we introduced this infinite and periodic crystal. But then this means that, as Shobana was mentioning before, is that the condition of having vanishing forces is not anymore sufficient to have defined the equilibrium, for instance, the zero temperature equilibrium geometry of a system. Because now the configuration is defined by the collection of the atomic position inside the unit cell and the definition of the unit cell. So the atomic position can be defined either using, say, Cartesian coordinates. This tau are the Cartesian coordinates of atom S, and alpha is the Cartesian coordinate. Or one can use express this as a linear combination of the fundamental lattice vector of your Ravel lattice. AK alpha are the fundamental lattice vector of the Ravel lattice, so these are three-dimensional vectors. And then X, S, K are the projection of the Cartesian coordinate on the Ravel lattice vectors. In order to find the static equilibrium, you need not only to have that each atom do not experience any force, but also that the cell the cell of the system is not under any stress. Okay. So stress, as was mentioned before, is something that you can find when you think of an homogeneous deformation. So you have your system and you deform, adding some stress tensor strain tensor to your position, and then the stress is defined as the derivative of the negative of the derivative of the total energy with respect to this strain. first order derivative, so applying the Hellman-Feynman theorem in the general way that Stefano Baroni was mentioning yesterday, one can demonstrate that there will be no need of looking for derivatives, variation of the parameters that defines your energy, except the direct dependence of the energy on the parameter you want to take the derivative with respect to the one you want to take the derivative. So this means that when you think of calculating the stress as a finite energy difference between a cell, the equilibrium cell, or let's say the starting cell, and a deformed cell, in principle, the electron will readjust, but also the atomic position inside the cell in general will readjust. So when you have your system, you deform it, and even if in the starting configuration the atomic position were the equilibrium position for that particular shape, so when you change the shape, then in principle those positions, the transformed position, are not anymore the equilibrium one, and so in principle one should include, one can think that one should include this contribution in the stress. But since we are interested in a first order derivative, and we are interested in first order derivative of an object which is variational, then all the implicit derivatives, so the one with respect to the electronic coordinates and the one with respect to the ionic internal degrees of freedom, can be shown to be 0. And so, so there is no need to know how electron readjust when you deform the system. There is no need to know how the internal coordinate would change. The electrons will readjust, electronic coordinates, internal coordinate will change, but there is no need to know that in order to calculate the stress. So the stress can be computed from the ground state wave function, assuming that the ionic coordinates are deformed homogeneously. And so, I don't give any formula, but the formula were given by Nielsen and Martin in 83, 85 papers. But the basic idea is that this is, as for the forces, a first order derivative of a variational function, and so can be calculated without need to knowing how the electrons and the ions readjust. In the code, WSCF code, how do you tell the system to calculate stress? Simply you have to specify this variable, T stress equals true. If you are doing a self-consistent calculation and you want to see the stress tensor at the end, then you have to specify this variable. If you are doing a variable cell minimization cell or a variable cell molecular dynamic calculation, then this variable will be set automatically, so you don't need to specify. Okay, so this is basically the input we had yesterday for silicon. There are a couple of variables that you didn't set yesterday because are automatically set actually in your computers. So, which is a directory where the pseudopotential files can be found, and a directory where some auxiliary files that the code produce can be stored. And in particular, this one, these two variables, these two things are not used in your input because they are set through environable variables in your case, and in particular, this one is set on the local scratch, so that you avoid writing through NSF and then get stuck as yesterday.
No, but it's not the problem. I mean, it is not writing these files into NFS.
No, it's not. But if you are using the local PMP, then it does not use NSF. While if you are using the local home directory, which is mounted through NFS.
Okay. No, I mean in the labs it is set up already to use the TMP directory.
Exactly what I was saying. So you don't need to do that, and because it is automatically done in such a way that it uses the TMP, which is a safe choice in our case. Okay, so this is the input, basically the same that you saw yesterday at a lattice parameter which is close to the equilibrium geometry, and then if you run it, since we said that we wanted to see the stress, so at the end of the calculation, after the total energy is printed, then it will print the stress. And if you see this one, okay, this is in Rydberg atomic unit, and this is in kilobar. Okay, so it's seems huge, but it's not very big, and it is negative, which means that the system would like to contract. So the calculations say that at 10.20 bore radii, the stress is negative, and so the system should contract. If you calculate the total energy for a several number of key points at 16 Rydberg, then this is what you get. We are at 10.2, and so you actually would say that the minimum is somewhere between 10.2 and 10.3. And if you calculate the stress, this thick line is what you get from the calculation, and the thin red line is what you get if you interpolate an equation of state through these points, and then you take the derivative of the equation of state, and so correctly the equation of state, which is derived from these points, tells you that the equilibrium geometry, so the place where the stress should be zero, is somewhere between 10.2 and 10.3, while the directly calculated stress, that should be the right thing to do, because it is exactly calculated from the functional that you have at that cutoff, etc., then it gives a result which is way off from that value. So what's wrong? So there is something wrong. What is wrong? Well, what is wrong is not as much the stress, nor the particular energies that we are using, but it is the fact that actually if you were doing a calculation with many more points in the lattice parameter sweep, then you would see that actually the function that we are trying to, we are looking to find the minimum, is not very regular. So it's a function that is continuous for a while and then has sudden drops, and the stress that we calculate is actually the derivative of the function of this function in the region where it is continuous, and then it is meaningless where it is it has sudden jumps. So for a denser grid, what you get, and indeed what you see is that at 10.2, actually this one, yes, the curvature, this curve is actually increasing. So actually the system tends to or here also. So the pressure correctly say that the system should reduce its size. The problem is that what we are interested in is actually the general behavior of the core. So why the energy is so irregular? Well, the problem is related to the fact that we are using plane waves, and these calculations are done using a constant cutoff. So when you have a certain cutoff, you have your Bravais lattice, you have the reciprocal lattice. This is, let's say, the reciprocal lattice for a cubic system or a square system. And our recipe is that our basis set is corresponds to a set of plane waves whose cutoff energy, so whose square moduli, are less than a given cutoff. And so these are the one inside the sphere, the one inside the circle, are the plane waves that we are using for the calculation. And they are spaced with basically by 2 pi over 8. Suppose you expand a little bit. So as Shobana said yesterday, the Bravais lattice and the reciprocal lattice are conjugate in some way. So when you expand the Bravais lattice, the reciprocal space contracts. So if you expand it by 5% or something like that, then this is the new set of plane waves. And what you have is that some plane waves that previously were outside your basis set, like this one, that one. When you expand by a little bit, they get inside your basis set. So suddenly, due to the discrete, the fact that you are using a discrete, a finite cutoff, and the fact that we are using a finite set of key points, then basically the basis set that you are using at different lattice parameter may change. This doesn't change always, because then if you expand a little bit further the lattice parameter, for a while nothing changes until you start including this plane waves, for instance. So, but from time to time, the number of basis function will increase suddenly, since this is a variational problem. When you increase the variational freedom, the energy will suddenly become better, and this is what happens here. So when new basis function enter in the calculation, then you have sudden drops in the total energy, and so these sudden drops in the total energy associated to the increase of the basis, the number of basis function, interfere with the minimization of the minimization process that we want to do. So why? So one can think that there is a simple solution to that, is that we shouldn't do calculation at fixed number of at fixed cutoff, but we should choose a set, a basis set, and then keep it at all for all configurations, and that's fine. So for instance, let's take the set of plane waves that we can identify at 10.2, and which corresponds to 289 or 283 plane waves. These calculations are done with 2 key points, so we have actually 2 different number of plane waves, one for the first key point and one for the second key point. So suppose that we keep those plane waves and we follow them while we are changing the lattice parameter. That's fine. The curve is smooth, so the thin curve is so the thick curve is the previous one, and the thin curve is smooth, and the derivative now is the derivative of the thin curve, and the minimum is in the right place. This is fine. The problem is that the structural properties that one can get from calculation done with fixed number of plane waves are more sensitive to this number, so converge more slowly than with respect to the dimension of the Bell set, with respect to what you get when you have a cutoff, a fixed cutoff. So basically, choosing a fixed cutoff corresponds to choosing a minimum wavelength that you are describing correctly. So any feature which is smaller than this wavelength is treated incorrectly. But somehow, so when comparing different different structures, if you compare quantities computed at the same cutoff, you are comparing energies that are computed with the same spatial resolution, so using the same minimum wavelength in the different configurations. While if you are using fixed number of plane waves, then the bigger becomes the bigger the cell, the larger is your minimum wavelength. So you are making a better job for small lattice parameter and less good, a worse job for larger lattice parameter. And this is why actually the minimum that you find at fixed number of plane waves is always an underestimation of what you would obtain by interpolating the calculation at fixed cutoff. So instead, what happens is that if you calculate at three different parameters, so if you calculate at three different cutoffs and correspondingly to a three different number of plane waves that more or less corresponds to the other calculation for 10.2, then what happens is that you see that the calculation, the stress vary significantly. At least 16 definitely is not a good choice. 16 Rydberg is not a good choice for this system. While if you are making the fitting of the total of the energy calculated at fixed cutoff, and then you interpolate and you find out the minimum by interpolation, then more or less the minimum is much more stable. So in the end, the problem is that calculation at fixed cutoff usually gives you better converge faster to the right answer, so converge faster to the value that you would obtain for very large cutoffs and very large number of plane waves. They have this additional problem that when the cutoff is not enough, it is not large enough, the curve is irregular, and so typically you need to make this interpolation. But you see that this irregularity goes away when you converge your basis set. So if you want to use, and this is what you typically want to use when you want to do more complex systems, where you need to also optimize the cell shape and so on. So if you want to use the stress in order to drive search for the equilibrium geometry, it's important to remember that you need a larger cutoff with respect to what you usually would choose if you are only interested in the energy, because of the fact that at lower cutoff the energy versus volume curve is irregular. See. So, as I said,
my question is,
yes.
So is it true that the reason for this is because you throw away the pooling terms?
No. The problem is that you are changing your basis set. So the problem is that the derivative of the derivative is correct in the sense that this object is really the derivative of this continuous function. The problem is that this continuous function is not what you want. You would like the one that interpolates smoothly. So now I will say something more on that. So, as I said, calculation at fixed cutoff usually needs some interpolation in order to extract the structural parameters because they are irregular. They converge typically faster to the result that you would obtain at convergence. The problem is that they converge faster with respect to what you would get for fixed number of plane waves. So one usually says that complete convergence is needed in order to have accurate calculation of stress. This is not really true, in the sense that the stress is calculated accurately, but is the accurate derivative of a function that is not the one that you would like. Is a correct, accurate derivative of the irregular function. So rather it is that you need good convergence before the calculation of the stress that assume a fixed number of plane waves agree with a smooth interpolation of the energies. And this happens because when the cutoff is large, the smooth curve that you obtain at a fixed number of plane waves becomes closer and closer to the calculation that you obtain at fixed cutoff.
I have a question. See, if you start choosing the cutoff from say 16 grid bar to
Right.
326 grid bar,
Right.
and looking for a smooth landscape.
Yes.
Now there is no end of it. For example, how do I know this is physical, right? So suppose I start from 10 and I end up in 800 to look for the smooth. But such a large variation has some.
Yeah, I mean, you do not need to go to 800.
Because you see here, I can clearly see from 16 to 326,
Right.
there is really a difference. Now
Yes, but there are two things here. No, there are two things. One is that by increasing the cutoff, you increase the variation of freedom, and then everything goes down because we have the variation of
No, it's not 326, is it?
No, this is 16, 24. Oh, no, sorry. Sorry. No, this is 32. Sorry. No, this is not 300. This is 32. So that's my fault. I made an error when putting the label. No, this is 32. So 16, 24, 32. Sorry. No, 32. This is correct. So 24 is already good because so there are two things. One, by increasing the cutoff, everything goes down for variational principle, and then everything gets smoother. And it becomes smoother because the extra the inclusion of extra plane waves that suddenly occur will keep occurring, but these extra wave functions at a certain point will not be important anymore, because if the system is already converged, then you have more variational freedom, but that's it. I mean, you are already very close to the minimum. So these sudden jumps is what you see them when you are still far from convergence, and adding a few more degrees of freedom helps you minimize it better. When you are already almost complete, you add a few more plane waves, and that changes. So by increasing the cutoff, the curve, the green, the thin and the thick curves that corresponds to one is continuous, corresponding to fixed number of plane waves, and one is irregular, corresponding to constant cutoff. These two lines tends to become much closer, and at 32 you are distinguished. Okay, so and in this sense, you need a complete convergence in order to have accurate calculation of stress. In the sense that you need good convergence of your Bessel set in order for the accurate calculation of the stress calculated at a fixed number of plane waves to agree with what you would obtain from an interpolation of the constant fixed cutoff calculation. So,
yes, in this case, for example, in case of silicon,
yes,
this 32 where you have achieved this smoothness in the curve corresponds to something like 2.7 electron volt.
32 is 400 electron volt or something like that.
13.6. So 400 electron volt. So 400 electron volt energy
this is the kinetic energy of the highest kinetic energy that you are allowing for your system. So the highest,
But the crystal lattice usually exists with the energy, for example, if you look at the silicon ionization energy.
Yes.
Something like 8 to 9.
No, but this is related to the. It's related to the sharpest feature that you want to describe in your wave function. It's cutoff that is related to wavelength. So this is corresponds to the shortest wavelength that you are describing in your.
Yeah, someone asked me this question. I could not really physically explain.
Why 32?
Why?
Or why whatever. Roughly, it is related to the atomic sign. It's related to the wave function has a variation which is of the order of the core radius. So the larger the core radius, the smoother will be the wave function, the lower will be the cutoff meter. But then, depending on how the technicalities of how you generate the pseudopotential, then you may have for the same element pseudopotential that converge at 30, pseudopotential that converge at 50. So, it's really comes from the Fourier transform of the atomic wave functions. So you take your pseudopotential in the radial grid in your atomic form, so you do not have any plane waves or anything. You take your wave function in the radial grid, you make the Bessel transform, and this gives you the Fourier transform in the radial grid, and then you see where this Fourier transform decay. This is for the atomic wave function. In the solid, it will be a little bit different, but it will not be so much different. And so if you see that your wave function die at 30 Ripper, you should more or less have this. So you would expect this to be the cutoff in the calculation. And this obviously depends on how the pseudopotential was generated. So the wave function is a fake object. It's not a fake. It's an auxiliary object that we are it's fake, but reproduce the right properties, but how well it does and how many plane waves you need to include depends on the details of the generation. So difference in potential may mean different cutoffs.
So other query related to this, most of these calculations we tacitly say that this is zero temperature calculation.
Right.
The question is, at zero temperature, why the system acquires such a high kinetic energy?
Well,
This was also a very question.
not all. I mean, there are. Let me go on a little bit, and then maybe we can discuss this. The main point, and maybe it's related to your last question, is not the kinetic energy. I mean, low-lying states will mainly be smooth, but will have some contribution from large highest plane waves. So the wave function will still be mainly smooth, but if you add some variational freedom and some shorter wavelength, the wave function will say, why not? I can try, and if it is a good one, it will include it in the calculation. So the problem of this disagreement between the derivative and the interpolation of the wave function is related to these irregular jumps. So if we can find a way, a trick by which we can smooth out these jumps, then the derivative, then we will have a continuous function also at fixed cutoff.
But I think the answer to his question, he was asking why at zero temperature you have a high kinetic energy.
No, but
I mean, it's because of the, if you like the Pauli exclusion principle, if you have free electrons, then you only have kinetic energy. But even at zero temperature, you occupy up to the Fermi level. That's because they don't all just have zero energy.
yeah, but you don't get to 32 rhythm. I mean, so the problem is that the potential is mixing the low line frequencies with the high cutoff.
That's my question. For real physical system, even metal, 10 electron volt is the Fermi energy. You need not have to have 400 electron volt, which seems somewhat unphysical.
This is a hydrogen wave function. Hydrogen wave function has a cusp at the origin. In order to describe this wave function, you need very high Fourier components.
Increase the curvature, right? If you include a higher kinetic energy cutoff, that allows your wave function to have a sharper curvature. So if the wave function goes, rapidly to zero or something at some point, then in order to describe that correctly, you need a high kinetic energy cutoff, sort of, right? So the softer the potential, the lower the cutoff you need. So needing this high cutoff doesn't have to do with the actual kinetic energy of the electron to the ground state. It's just a basis set error. Because the basis that we're using is just a way of diagonalizing a Hamiltonian that we can't find eigenstates of exactly. Right? So it's just a basis set issue.
Yes, it's related to the fact that the pseudopotential couple different plane waves. So couple the plane wave of your, your low line levels will be mainly smooth, but they will have components at high kinetic energy because the potential energy couples the different vectors. And the harder is the potential, the higher will be the plane waves that are connected. But what I wanted to say is that these jumps are related to the fact that when new plane waves are added, they matter. When the new plane waves are included, they give some advantage. And so, by including them, you reduce sharply the energy. So you can kind of prevent this, or you can try to make things smoother by modifying the energy in a way that when you suddenly add new plane waves, they do not matter so much. Okay? So one thing that we can do is to kind of modify artificially the kinetic energy part of the Hamiltonian in such a way that the kinetic energy, fake, artificial kinetic energy associated to a G vector is not the, is the true one, plus something that above some fixed of energy will add a step, a smooth step, in such a way that, so there are two cutoffs now here. One is the real cutoff for your calculation, so the one that set how many plane waves you are including in your calculation. And then another cutoff, which is this EC fixed, that basically is the place, the energy at which you start penalizing very much the new the plane waves that have kinetic energy higher than this EC fixed. Okay. So what happens? All the plane waves that are below this EC fixed just experience the usual thing. All plane waves that are above have a penalty which is very large, or can be very large if you give a very large number to this Q cat Z. So even if you include more plane waves, if these are all above SE fixed, then these new plane waves will be penalized by this quantity. And so in the variational principle, they will cost so much that they will make a very little contribution to the total energy. What is gained here? Well, what you have gained is that the plane waves around and beyond EC fixed, not the cat, sorry, EC fixed, are penalized so much that they do not matter. This seems a stupid thing, because we are actually including plane waves and then we are not using them. That's true, but the nice thing is that when they start matter, you can take into account their contribution in a continuous way, because this is a continuous function, and so they start, and so you can take derivatives of these objects. So when you take derivatives, the fact that plane waves that used to be above XE fixed and start to be below XE fixed, they will give a smooth contribution to the total energy. So we have, if you want, disentangle the problem of including new plane waves and including effectively new variational variables. So by doing like that, and if Q cat Z is large, when you add new plane waves, this doesn't change much. And then when these new plane waves, by taking larger and larger cells, start becoming below SE fixed, then they start contributing, but they start contributing in a way that can be differentiated, because this is a continuous object. The way you specify this is like that, for instance. So you have a cutoff, you are doing calculation at a given cutoff, let's say 18, and then, but you start, let's say you start penalizing a lot, so 30 Rydberg penalty, to basis functions whose kinetic energy cutoff, whose kinetic energy is larger than this EC 16. And then you have smoothing parameter. I mean, this step function means actually something which has a width, a finite width of the order of 2 Rydbergs. All the rest is the same. So what happens? What happens is that the curve now is this green one. Okay? So we have a calculation that is done at 18 Rydberg. Include all plane waves up to 18 Rydberg, but give a penalty to all plane waves that are above or around 16 Rydberg. Actually, already 16 Rydberg, the plane waves are already penalized. This is why this curve is above the red one. Okay, so the at 16 Rydberg, you are already adding a penalty, and so the total energy is larger. What is nice is that now this curve is smooth, and the derivative of the green curves can be calculated analytically, and they agree, and the minimum is where you expect it to be. Yes?
What's the scale of the y-axis?
Energy, Rydberg. Rydberg. Sorry. And these are Bohr radii. Okay. So, if you want to calculate pressure and you want to the best thing is that you increase the cutoff. And then you increase the cutoff up to things are smooth and everything is fine. If for some reason your system is so big that you cannot afford a very big cutoff, etc., and then you think that some smaller cutoff should still be reasonable, but you have this problem of irregular functions, then you can use this trick in order to smooth it. And you need to know that this is a trick so that you are making an approximation, but this may be useful to gives you a reliable relation between energy and I mean, it helps you to have a smooth energy versus volume curve even at somewhat lower cutoff. Okay, at finite pressure, if I want to optimize or sample the system, then the appropriate function to sample is not the energy but the enthalpy, which is the energy plus PV, and this can be done using variable cell relaxation if you want to optimize, or variable cell molecular dynamics if you want to make some study some finite temperature property. Variable cell relaxation, in reality there is not much to add to what was already said previously. What is implemented in our code is BFGS relaxation. One of the schemes which is implemented is BFGS relaxation. The only thing that you need to remember is, well, you don't need to remember, but the only thing that the code does is to take into account the fact that the crystal configuration is defined not only by the 3 times number of atomic coordinates, but plus the 9 variables that define the Gravel lattice vectors. And the algorithm can be applied, it's very general. BFGS is not specific of any DFT calculation. It's a minimization strategy, so it's very general. What you need is to calculate the appropriate, so define your variables and calculate the appropriate gradients. The derivative of the enthalpy with respect to the internal coordinates in crystal coordinates is something, some linear combination of the forces multiplied by the Gravel lattice vectors, and the derivative of the enthalpy with respect to the Gravel lattice vectors is something related to the stress minus the external pressure that you are imposing times the inverse of the well-lattice vectors matrix and the volume, and so on. So you need to define properly, to define the appropriate correspondence between your functions and your variables and your gradients. And the next thing that the other thing that you need to do if you want that your relaxation preserve the symmetry is to start with an inversion that has the symmetry that you want to preserve. And so this is something. So usually one starts in the usual case where Ravel lattice vector are not included, once and Cartesian coordinates are taken into account. One starts from a diagonal Hessian that contains no information. If you do that directly in the variable cell, then this actually is not the appropriate choice because it does not respect the symmetry of the system in when you are using this derived variables, but there is some choice that respects the symmetry and its work. So basically, BFGS relaxation can work the same way. This is one case that we will also see this afternoon. This is arsenic. Arsenic, the element, has a A7 structure at zero pressure. This A7 structure is a rhombohedral deformation of the simple cubic lattice. So when you actually squeeze the cubic, the simple cubic along the 1 direction, then so that the cosine between two vectors becomes less than 60 degrees, then the arsenic will show this structure at zero pressure, and instead above a certain pressure, which is of the order of 20 or 30 GBA, so 300, 400 kilobar, it will go back to the cubic system, to the cubic cell, in which this angle is 60 degrees. So the input, let's say, for an arsenic variable cell relaxation at zero pressure is like that. You need to specify what type of calculation you want to do, and you say VC relax. Then you don't need to specify anything of this because they are already set by environment variables in your case. Okay, then you specify the threshold for convergence for the energy and for the forces. So the calculation will stop when energies between subsequent estimate of the relaxed geometry is less than 10 to the minus 4 Rydberg, and the forces are less than 10 to the minus 3. And then there is another one, another check on stress. So when the stress is less to, I think, half a kilobar, I think, if I remember correctly. This is the default value, and then this is the definition of the system. It has 2 atoms per unit cell. We are using I grav equal to 0, and we are specifying the lattice vectors. And since we are saying that VC relax, so we are specifying that we want to change also the cell shape. So there is one more, in addition to the ions name list, there is a cell name list that need to specify, where you need to specify variables related to the cell. In this case, we just specify the pressure at which for which we want the system. and then this is just the definition of the atomic species in the system, and the position of the atomic position in the system. And then we are using 444 shifted Monko-Spack acceleration.
What is the energy convergence criteria? What does it do?
It stops, I mean, this does a series of self-consistent calculation, and it will stop when all three, when three conditions are met. The energy between the energy difference between the last configuration and the previous one is less than 10 to the minus 4. The forces on all atoms is less than 10 to the minus 3. So any component of the force, all components of the force have to be less than 10 to the minus 3. And the pressure, which is not there because there is a default value, the pressure is less than 0.5 kilobar.
Yeah, the reason I'm asking is that it seems that the stress and the force should be enough, right? If you get the step.
Usually, actually, you are right in the sense that this one is usually met much after this one. So this one, in the end, doesn't matter because the energy vary very little. When you are close to the convergence, it's hard to reduce all forces below threshold while the energy has already converged. This is true.
Yeah, for zero stress and zero force, that would define the geometry, right?
It's true. I mean, you want to be sure. Anyway, there are three conditions. So on the energy, on the force, and on the stress in this case, and the one on the energy is usually the one that is met first. So it's not really relevant, but put it anyway. Okay, so if you do this calculation and then you run it, after a while you can produce an output which is huge, but you can look inside the output looking for enthalpy nu, so the new estimate for the enthalpy, the final estimate for the enthalpy, what is the pressure that you have, and and what you see is, for instance here, the convergence 10 to the minus 4 in the energy would have been met somewhere here already, while the pressure is still varying, and then actually stops when the convergence is below 0.5 kilobar. And in this particular case, the forces are zero by symmetry, so they do not matter. But in general, when you have less lower symmetry systems, it's the real condition on the real stopping criteria that matters are the forces and the stress, because the total energy is easier to converge. I will not